Columbia chapter, Ice Age floods. And this is the third Thursday of October, October the 20th, 7 p.m. And our speaker tonight is Paul Loikith.
And let me share a little bit about Paul. I have never met him personally, but I'm seeing him on the screen. Paul is an associate professor of weather and climate science in the Department of Geography at Portland State University, where he directs the PSU climate. He earned his Bachelor of Science in Meteorology and a PhD in Atmospheric Science from Rutgers, that's New York, isn't it?
New Jersey.
New Jersey. And prior to that, joining PSU in 2015, he did postdoctoral scholarship at the NASA Jet Propulsion Lab. Where is that located, Lloyd? I mean,
that's in Pasadena, California.
Pasadena. Yeah. His research focuses on the drivers of extreme weather, which we know about now more around our country and world, how they are represented in climate models that we see often talked about on the TV, I guess, other people do their analysis, and how all these drivers are affected by global warming. So I'm so pleased that Paul could come. This is a very timely topic for us all. Everybody seems to be talking about the weather these days. And we know Ice Age folks remember, how we all learned about this through the glaciers covering the northern part of our nation, Northwest, lower Canada. And then those melted and created another kind of extreme condition. But now we have it right here in our own backyard, so to speak. I know I've had trouble with my own tomatoes this year, trying to get them to figure out what's going on with the weather after we finally got them in the ground. So welcome, Paul. We're glad to have you here. We will save questions to the chat, and both Paul and I, maybe Lloyd, will watch that chat down at the bottom of your screen, where you might be able to tap in that or wait to the end of Paul's presentation to ask more questions. Thanks, and welcome, Paul.
Oh, thank you. Thanks for having me, everyone, and thanks for the introduction. Can everyone hear me clearly?
Yes.
All right, I'm going to share my screen with my slides and get right to it. So it's kind of impossible to cover everything that's interesting and important on this topic in just one presentation. So I'm going to give an overview, kind of like what the title says, of climate change and weather in the Portland region, looking at some recent trends and then future projections based on the state of the science and what we think is going to happen going forward. And we'll kind of touch on some of the most important weather and climate variables that influence our day-to-day lives and influence things on longer time scales. I am going to have a lot of charts. I like charts and maps and things like that. I'm a quantitative scientist, so but we'll walk through all of these pretty carefully. My contact information is here, so you can always feel free to follow up afterwards. I'm going to start really basic. First, I'll just tell a little bit more about myself. Larry gave a good introduction, so I won't spend too much time on this. But my research, actually, it really was said pretty clearly in the introduction. I focus on the atmospheric drivers of extreme weather events. My background in meteorology comes out of a lifelong fascination with weather. And then I kind of got into climate science research at the climate timescale, so longer timescales in weather in graduate school. And I've kind of combined those two interests in my research and my expertise and my teaching. And I often like to point out that I'm a physical scientist. So oftentimes this topic there's a lot of questions and important things to talk about around policy or climate change solutions and impacts. And that's professionally not really where I have my expertise. So I will be focusing on the physical science aspects of this topic. And as Larry mentioned, I direct the Climate Science Lab at Portland State, which is my research lab. It's a teaching lab and a research lab. And this is who's in the lab. So this amazing team of students and postdocs. There's actually a postdoc who's not on here. So 2 people doing the postdoc with me, a couple of master's students and a PhD student. And they're working on all kinds of projects that are around the topics that I'll be talking about. We have a website here with more information on what we do. And our research is supported currently by NASA and the National Science Foundation. So that tends to be the world in which we are conducting our research. That's where we're getting our support. Topics that we're working on actively are involved looking at changes in extreme temperatures, which sounds like fairly basic. In some ways it is, but we're doing basic science research on there's still outstanding questions on why some places are seeing faster or slower increases in extreme temperatures than other places. We're looking into extreme events. So we just submitted a paper on the June 2021 heat wave for review. We're also looking at the 2020 Labor Day wildfire event, which I'm sure most of us remember from a few years ago, and looking at large scale weather patterns in the Northwest. And that's kind of a theme around a lot of our work. I'm going to start really, really basic with climate change because I often find that while a lot of people are thinking about this and we hear lots of information about it, and a lot of people are very concerned, I find sometimes not everyone has the foundational understanding of exactly why we're seeing what it is that's being talked about. And sometimes that actually leads to information that's not completely correct being shared in the media or being shared even by other scientists who aren't climate scientists. So I really want to take a step back and talk about the fundamentals of what is causing this problem, why it matters, and then we'll go into actually looking at things that it's doing. And I like to start with just this basic question of why climate change is a problem at a really high level, globally speaking. Not talking about any particular region. And this is how I think about it. The environmental condition that humans and other living things have adapted to over time, those conditions are changing faster than can effectively be kept up with. So the overall background of the environment we live in, which the climate is an important part of that, is progressively and steadily changing. Now, if the climate changed and that was it would give a target for adaptation. There would be problems, but things could adjust. Some things maybe couldn't adjust. But the real problem is it's a moving target. So it's not like climate change happened and now we have to deal with it. It's a process that's ongoing. And so that requires every living thing to try to keep up with these changes, and it's happening faster than is easy or even possible to do in some cases. I like this flow chart on the bottom too, and thinking about all the different terminology and different things that we hear about when we're talking about climate change. And I think about it this way. So this all starts with humans increasing concentrations of greenhouse gases in the atmosphere, which we're going to talk about in the next two slides. It might be review, but it kind of doesn't hurt to just go over the physics of why that matters. That leads to global warming. That's the term referred to as the planet getting warmer because of this change in concentration of these gases in the atmosphere. That overall global warming then causes climate change. It causes other things to change beyond just global temperature. It affects regional temperature in different ways than global temperature. It affects rainfall and snowfall. It affects things like the sea level. It causes changes to the ice storage on Earth and so on. So that's climate change. That's more encompassing than global warming, which is really just referring to temperature averaged about the world. That in turn has impacts on humans and natural systems, which is what has kind of recently, relatively recently, come to be known as a climate crisis. So the crisis is the result of this over here on the left. Sometimes I've heard the climate crisis is causing something, but I kind of think like it's the actual effect that's the crisis. The cause is global warming. And then you could go a little further into management and mitigation of the problem. And I have these two, global warming and climate change, highlighted in these red boxes because that's where my expertise lies, much more so than on the other sides of these two topics. All right, we're going to step really back to basics and just go over the fundamental physics of why global warming happens, and actually just why the Earth has the temperature that it has in the first place. And this is just kind of greenhouse effect 101 without equations. We could put equations to all of this, but we'll just do this qualitatively. So we have a really simple model here that I sketched out where we have the sun and then we have the Earth here at the bottom, this green line. The sun sends energy towards Earth's surface in the form of relatively short wavelengths. So the wavelength of energy is proportional to the temperature of the object emitting that energy. So the sun is emitting very hot, it's emitting at a very hot temperature. So the energy that Earth receives from the sun is at short wavelengths relative to what a cooler object would emit. It's also important to remember that a warmer object emits more energy than a cooler object overall. So Earth receives this energy from the sun, but 30% of that energy is reflected immediately back to space and it doesn't do anything for Earth at all. It doesn't get absorbed by the oceans or the surface or the atmosphere or anything. And that's reflected by bright surfaces, primarily by clouds, then also by snow and ice and other reflective surfaces. So 70% of what the sun sends our way is absorbed at the surface, into the ocean, into the land surface. And then Earth emits that energy back to space, and it must emit the same amount of energy it receives from the sun. Any object in space must be in this radiative equilibrium, where it is emitting the same amount of energy it's receiving. Earth is cooler than the sun, so it emits this energy at longer wavelengths. In this model, if this was the only things that we were considering, and we applied equations to this, we would come to a global average temperature for Earth of negative 18 degrees Celsius. So we're obviously missing something fundamental because Earth would be completely covered in ice. That's not the actual temperature. The actual temperature is about 16 degrees Celsius. So you may have guessed that we're missing the atmosphere. That's the important component that we didn't include in that previous simple model. So we have the same thing going on with the sun sending relatively short wavelength energy towards Earth. 30% of that's being reflected primarily by clouds, but also by snow and ice and other bright surfaces. The rest gets absorbed at the surface. And Earth's atmosphere is almost entirely transparent to those short wavelengths. So that energy not much of that energy gets absorbed by Earth's atmosphere. There's a little bit of absorption in the stratosphere due to ozone, but most of that reaches the Earth's surface and warms the planet. And then Earth has to emit the same amount of energy back to space that it's receiving from the sun. But now in this model, we've added a more complicating factor. In the atmosphere, there are gases, because of their molecular structure, that are really effective at absorbing energy in these longer wavelengths that Earth emits towards space. So carbon dioxide, water vapor, methane, and a few others, those are called greenhouse gases because their presence breaks this radiative equilibrium. So you no longer have the Earth emitting the same amount of energy to space as it's receiving from the sun, because that energy that Earth is emitting towards space, a lot of that is being absorbed by these molecules. Then those molecules emit that energy in all directions. Some of that energy gets absorbed by another greenhouse gas molecule, and then that gets emitted, and some of that gets absorbed by another greenhouse gas molecule. Eventually, that energy is emitted back to space from a higher level in the atmosphere, which is a colder level. But Earth is not in radiative balance because it's receiving energy from the sun. It's 70% is reaching the surface, but it's not able to emit that directly back to space. So going back to the previous slide, remember a warmer object emits more energy. So Earth must be in radiative equilibrium. So since that's broken by the presence of these greenhouse gases, how does Earth regain that radiative equilibrium? It gets warmer, because if it's warmer, it emits more energy. So Earth warms to the point where it's emitting enough energy to space to balance what it's receiving from the sun. And anytime you change any part of this simple conceptual model, the global temperature also changes. So if we made Earth icier, more than 30% of the energy from the sun would be reflected. Earth would cool. It's not receiving as much energy from the sun. If we increase these greenhouse gas concentrations, Earth would warm because less energy would be able to go directly to space. Earth would have to warm to emit enough energy to balance what it's receiving from the sun. And that's what's happening with global warming, because humans are causing particularly this gas, but others, to increase unnaturally in its concentration in the atmosphere, primarily through the combustion of fossil fuels, carbon-based fossil fuels. There are other greenhouse gases that humans also influence, like methane, and then these as well. And these, except for water vapor here, are long-lived greenhouse gases, which means that once we emit them, they're up there for a really long time. So they affect Earth's radiation balance for a really long time. Water vapor doesn't stay in the atmosphere very long. Its lifetime is about 7 days. It rains out once you get more water vapor, but if water vapor increases, the greenhouse effect also increases. So that's the physics behind global warming. It's super simple. Climate change is super complex. It's not simple at all, but global warming is really simple. The physics has been understood for a very long time. In fact, I think my next slide talks about this. The physics has really been understood since the 1800s. It's been modeled by computers since 1975 at the NOAA lab in Princeton, New Jersey, Geophysical Fluid Dynamics lab. Humans started altering the greenhouse effect by unnaturally increasing the concentrations of carbon dioxide in the atmosphere in the 1700s, but it took a while for that to be enough to create a measurable change in global average temperature, and that started showing up about the middle of the 20th century and then accelerated from there. This has been scientific consensus and well understood for decades, but scientists are still working on understanding the complexities of climate change, but that humans are causing global warming has been scientific consensus for a very long time. So it's not a newly discovered problem, even if I think some of the public interest and recognition of this has increased really in the last, I'd say 6 to 10 years. It's been a huge increase. Okay, let's just look at some evidence of what we're talking about here, because we can measure this with at least modern instrumental data. And we have really great measurements of carbon dioxide concentrations in the atmosphere. This is measured at the top of the Mauna Loa volcano in Hawaii, the Mauna Loa Observatory. This is called the Keeling curve, named for Ralph Keeling, who started this in the late 50s. And so we have this great record in the free atmosphere away from any local emissions of carbon dioxide. So if we did this next to Portland Airport, this would be ridiculous. Every time a plane took off, you'd see some carbon dioxide increases. So this is way up in the free atmosphere. It is in the northern hemisphere. And that's why you see this, the actual observations are this red line, and they're really jagged, because in the northern hemisphere, we have a lot of land with a lot of plants, and those plants die in the winter. Those plants are made out of carbon, and that carbon concentrations go up in the winter. And then in the spring, when those plants bloom and the flowers bloom and the plants grow, they use carbon from the atmosphere to do that. So that up and down is that natural kind of breathing of the northern hemisphere. When concentrations are measured in Antarctica, for example, you don't see that because the southern hemisphere doesn't have enough plants. So that's what we're seeing. The red and the black line is just smoothing that out. So we can see concentrations have been increasing steadily and actually at a more rapid pace as we go later into this record from the late 1950s onward. And I matched this up roughly with measurements of global average temperature, with each black square being 1 year's temperature. You see lots of variability. Some years are warmer than other years. Some periods of time are cooler or warmer than other periods of time. But the overall trend is undeniable, and it very closely matches the increase in carbon dioxide. Now that's kind of seeing is believing, but scientists, it's not like that's how we know that this is happening. This is a necessary response to this. So I think that's really important. So we want to see evidence. We want to be convinced by seeing evidence, but the physics tells us this has to happen. This isn't like a hypothesis and that we say, oh, look, it's happening. The physics that we understand says this has to happen. Although when Keeling started measuring this, it was not to monitor global warming, and people were surprised to see how this was increasing. And then they kind of put the connection together that this is happening because of human activity. Now, there's a lot of things in the atmosphere that affect the climate, and a lot of them are human contributed. And this is a fairly complicated chart, but there are a few things I want to point out that I think are really important and pretty interesting. On the left-hand side here is this vertical bar that shows the overall observed warming, global warming that is, relative to 1850 to 1900. So that 50-year period. So globally, the Earth has warmed about 1.1 degrees Celsius in the most recent 20 years compared to that 50-year period. There's an error bar on that because there is some uncertainty with observations. So could be a little bit less, could be a little bit more, but it's about 1.1 degrees. So where did we get that warming relative to 1850 to 1900? What contributed to that? And so scientists have estimated the contribution from all these different constituents that are understood to affect global climate. So the total human influence is this red bar. And look, it's virtually the same as the gray one, although the error bar is quite a bit larger. And that's because it's made up of all of these different constituents, some of which have larger uncertainties. So well-mixed greenhouse gases, that's another word for these long-lived greenhouse gases. They're well-mixed because they stay in the atmosphere so long that they end up evenly distributed across Earth. So local emissions of greenhouse gases are not important for local climate change. It's global concentrations that are important for climate change. So that's why well-mixed greenhouse gases are key. So if you have lots of greenhouse gases emitted in Portland, that affects the climate in Australia just as much as it does in Portland. So these are the really important ones. So those have actually added more warming than we've actually observed. So why is that the case? Well, we see this blue bar showing there's actually some other human drivers that have caused cooling at the same time. Here are the two natural drivers of global climate, global temperature, solar and volcanic drivers. Zero. Internal variability, that's just random fluctuations like El Nino and La Nina events, things that happen naturally, also centered on zero. Carbon dioxide is a big one. That's contributed a lot of warming. Methane contributed also quite a bit of warming. We have some smaller concentrations of trace gases here that have added some warming. Nitrogen oxides have added some cooling through some chemical reactions that remove some of the greenhouse gases. The really interesting thing here in the blue is the cooling caused by sulfur dioxide. And these are particles in the atmosphere emitted through industrial processes that reflect solar energy. So this is what causes industrial smog. So in places with a lot of unregulated industrial activity, like in Southeast Asia, or over North America and Europe before the Clean Air Act, there was a lot of sulfur dioxide and some other particles, and that reflects solar energy, and that contributes to cooling. So it's a little bit ironic to think that if we cleaned up the harmful to your health air pollution in the air, which is this stuff, we would actually cause global temperatures to go up even more. And so that's taken into account when scientists make projections of how global climate will change in the future. But that's also why well-mixed greenhouse gases are causing more warming than we're actually observing over this period, because there's been cooling effect from these reflective particles. Now, these reflective particles are terrible to breathe. So if we clean them up, it improves human health. But they're also very short-lived. So if we were to stop emitting these, like some parts of the world have through regulation and through deindustrialization, reduce the emissions of these reflective particles, they go away really fast. It's kind of like the smoke we have had here in the Portland area over the past couple of days. It seems like the smoke's with us forever. It's coming straight off a fire, so it's hanging out. But that smoke's going to blow away, and it's not going to be in the atmosphere in two or 3 weeks. The particles will rain out, they'll fall out, they'll be deposited on surfaces. And that's what we're talking about here. So carbon dioxide, once it's emitted, it's up there essentially on human timescales we care about pretty much forever. Some goes into the ocean, some goes into other carbon sinks, but what stays in the atmosphere is up there for a very long time. This stuff is up there for a very short time. So if we remove this, we would actually get even more warming, but improved air quality, better air for humans to breathe. So kind of interesting and rather complex. And you can see the error bar is quite large on here because particles do weird things to clouds and all kinds of other stuff that complicate the picture. Okay, so one way looking forward in time the primary way that scientists look forward in time to understand what scenarios are possible when it comes to climate change is using computer models that can simulate the Earth's climate and simulate how the Earth's climate changes when you change the radiative balance. Going back to this slide, basically you just change all of these arrows. It's a lot more complicated than that, but that's kind of the basic thing, and see how the climate responds. And so there are all these different scenarios. We don't know what humans are going to do in the future as far as emissions go. So climate models are run using very high emissions scenarios, and this is showing overall global temperature change over time. The black line here is observed temperature, and then going forward in time here, these are computer model projections. And then we have in this light blue color a scenario where humans stop emitting greenhouse gases really, really soon, and even start removing some from the atmosphere through technology. You see the temperature actually starts to cool by the end of the 21st century. So these are both kind of extreme scenarios. Neither are seen as very likely, but it's not out of the question that we would follow this one, but it's seeming increasingly likely. But I also like to point out on this, this green line is an approximate measure of how much global warming we've observed due to human activity to date. This red line, the length of that is proportional to the amount of global warming possibly projected under the worst case scenario by 2100. Look at the difference in size. This is how much we've experienced. This is how much we could experience under the worst case scenario. Again, that worst case scenario is seen as increasingly unlikely, not out of the question. But we're probably headed more on this 4.5 scenario at kind of the best estimates from the people who study this, but we don't know exactly what humans are going to do. So I showed this for two things. One, if this much warming has caused impacts, think about how much impact we get from that much warming. But the other side of the equation here is that we haven't really seen that much global warming compared to what we could. So there's a lot more change likely in the future than we had in the past, but that amount of change does depend on what humans do, where we theoretically could have only a little bit more change or a lot more change. One thing that is for certain is that we're not going to see no more change. Even if we stopped emitting globally everything right now, things would continue to warm for some time, and then they would plateau, and then we would kind of have a new normal for a long time. Some things that actually continue to change for decades to centuries. Sea level might even rise for centuries after warming stopped because there's inertia to the system. Okay, that's a global scale. Let's kind of talk more locally. I really like to think about climate change as changes in the probability distribution of some sort of variable. And I'm going to use temperature here because it's the simplest one. And temperature changes due to global warming are rather direct because as the planet warms, temperature everywhere just goes up. If we get to changes in rainfall, that gets more complex because the changes in rainfall are secondary change resulting from global warming and regional changes in temperature. So let's start with local temperature. And what I mean by changes in the probability distribution of temperature means a shift in the histogram. I don't know if histograms are things we're used to thinking about, but I have three histograms here. And the dark blue one is the histogram of temperature at Portland Airport for the years 1940 to 1967. So these are kind of equal chunks of time. And you can see that the temperature that occurred most often was here at the peak. This is about 65 to 67 degrees in the summer. This is daily average, so it's averaging the nighttime and daytime temperatures. And then you have these extremes where there were only a few days that were below 50 and a few days above 80. We don't see any dark blue even approaching 90. Then in 1968 to 1995, if we draw the histogram, it's this cyan color, and it's shifted to the right of the blue one. They have a lot of overlap. So most of the days that you experience in the next 30-year period, or roughly 30-year period, are within the range of what you experienced in the previous period. But you do get more temperatures on the warmer side of things. But we didn't actually see a big change in the extremes. They were about the same. But really hot days became more common. Now jump ahead to the most recent period, 1996 to the present. We don't see that much change, by the way, on the cool side of things, but everything has shifted to the right. And now we see, and this is thanks to June 2021, this drew the whole thing up to the right. A couple of days where the average temperature was in the 90s because of the so-called heat dome event in late June. But each time period here, the histogram shifted to the right. So you're still getting a lot of days that were the same temperature or the same temperature range as in the past, but you're getting more days on the warm side of the histogram and more days on the extreme warm side, or even days that are warmer than anything you observed before, and you're getting fewer days on the cool side. So it used to be fairly common to get days in the low 60s in the summer. Now that's much less common. It still happens, but it's progressively becoming less common. And we could do this exercise with other variables like precipitation. You could do this with like hurricane frequency. Not everything shifts, not frequency, hurricane intensity. You wouldn't see anything probably too much with frequency, but everything shifts some way, or the shape of the histogram could change as well. But I think this is important because I often hear climate change described as heat being added to the system, and that causes everything to just get chaotic and go crazy. And that's not really how it works. We're seeing a systematic shift in the overall average and the overall range of weather variables or temperature in this case. These dashed lines are the average, and you can see the average has been steadily increasing. So the extremes get hotter, the cool extremes get less hot, and the average marches upward. And in the recent 10 years, we've seen summers be extremely hot, which we'll look at in just a minute. Interestingly, for Portland, if we do this for the winter, actually I have these, just realized I have these animated so that we could look at one at a time. And I'm not running the animation because I'm not in presenter mode. And I'm kind of hesitant to do that because sometimes when I go into presenter mode, my computer freezes. So if you're okay looking at all three at the same time, I'll stick to that. I apologize. It's a little neater to see them one at a time, dark blue, cyan, and red. But we'll stick with them being all at the same time. This is winter for Portland. Notice how much smaller the warming is. The shift to the right is kind of hard to see. In fact, it was cooler on the extreme warm side in the most recent period than in the 1968 to 1995 period. So the average temperature in winter has been warming, but very, very slowly. This is not the case everywhere on Earth. Other places are seeing their winters warm faster than their summers, but in Portland, we are seeing our winters warm much slower than our summers. So we actually had more unusual warmth in the mid to late 20th century than we have more recently in winter. But what we have seen pretty clearly is a decrease and actually an elimination of extreme cold. We just don't get this extreme cold anymore. This over here is a major outlier. That was February 2nd, 1950. Portland Airport got down to -3 degrees Fahrenheit. So we don't see anything like that. It's not like that can't happen anymore, but it's becoming increasingly unlikely over time. Another thing I like to think about, I think that's important to think about, is really focusing in on the difference between weather and climate. And I think this is sometimes where things get missed a little bit in the public discussion. This is a crazy looking graph of every day's temperature in Portland going back to 1940. And it's just kind of total noise. You can see the seasonal cycle. So here's summers, they're warmer. Here's summer 2021. That's where we had the crazy heat wave. This is 1950 with the really cold weather. But we see up and down, up and down, up and down with the seasonal cycle, but it's hard to really see any clear change. So this is Portland's weather as defined by temperature. It's not really showing the climate at all. And weather and climate are different. Weather is short-term, climate is a long-term average of weather. But we can look at the weather by averaging every year's temperature together. So we started with this, we averaged every year's temperature, and we get this. Now we can see things about the climate. So we see climate variability. Some years are warm, some years are cold, some periods are cooler, some periods are warmer. And when we average the whole thing, we're using the standard 30-year averaging period of 1991 to 2020. We get this black dashed line, and that's kind of the estimate of Portland's temperature climate. So you can kind of see climate change here, but I'm not specifically showing climate change. So climate change would be a systematic change in the overall average of weather. You can kind of see that it was a lot cooler earlier and warmer later, but you mostly see a lot of variability. All right, let's hone in on climate change. So climate is not climate change. Climate change is exactly what it sounds like. It's a change in the climate. If we fit a linear fit to this time series of annual temperature, you can see this blue line, temperature has been steadily increasing. And that's climate change. That's the local reflection of global warming. And we still get cooler years and warmer years. 2011 was pretty cool, though it still was warmer than a lot of the cool years in the 50s and 60s. But overall, Portland has warmed by about 3 degrees Fahrenheit since 1940. And that's climate change. So year-to-year variability is not climate change. The average isn't climate change. It's that change in the average. That's climate change. And we can even remove climate change, or at least approximately remove it, by removing that trend. We can remove this dark blue line. And now we're left with what's just called natural climate variability. You see the year-to-year ups and downs, and we can see that there were periods of natural cooling, just because, mostly because of semi-unexplainable variations in the Pacific Ocean sea surface temperature, or other things that just happen naturally in the climate system. It was a cool period here. It was getting cooler. Then things are getting kind of warmer. Then things are cooling again until pretty recently when things started warming again. So if you remove that trend, then you can see the natural climate variability. Now, climate change and climate variability are both happening. Climate variability oscillates about an average. Climate change is a systematic unidirectional change. So sometimes you have climate variability and climate change working in the same direction. So recently, especially in summer, natural variability has been making it hot, and global warming has been making that hot period even hotter. But there are other times, for example, in the eastern US, this has been true, or the eastern half of the US, this has been true, where natural variability is working in the opposite direction of climate change or global warming temporarily and masking the rate of warming. So some places look like they're not really warming because natural variability would otherwise be making it a cool period. And when that natural variability switches over to a warm period, then you'll see temperatures increase much more rapidly. So these are happening at the same time. Sometimes natural variability looks like it's accelerating climate change. Sometimes natural variability looks like it's slowing climate change, but that's just the internal workings of the atmosphere going on at the same time that the temperature is increasing. Okay, let's look at precipitation. We've been talking about temperature a lot. This is Portland Airport rainfall for every day. I don't know, it's kind of a cool chart. You can see the seasonal cycle. You can see this dry summers in between the wet winters, but you can't see much else. There are some years that we had a pretty dry period here the past couple of years, and then it got wetter. We had some really wet years, but overall, it's kind of hard to tell what we're looking at because it's just daily rainfall. It's just day-to-day noise, just random weather. But we can look at the rainfall climatology by averaging or adding up the rainfall over each year and then computing the long-term average of that. So each green circle here is the total rainfall in inches for a given year. We get some really wet years like 1996. We get some really dry years. This was 1943, only 22 or 23 inches of rain over the entire year. We've had some dry years lately, and we've had some relatively wet years. So 2021 was actually pretty close to average. So this is a long-term average. So that's the rainfall climate for Portland. All right, let's do the same thing with climate change. You fit a linear fit to the precipitation data, it's almost zero. It's slightly negative, but it's so small it's not statistically significant. So there has been no observed change in our annual rainfall in Portland since 1940. Lots of variability, lots of wet periods and dry periods, wet years and dry years, no sign of climate change in our rainfall to date. Sometimes that surprises people, but that's what the data tells us. We'll look a little bit more at in just a few slides, like extreme rainfall and things like that, but the story is actually the same. All right, I like these charts. I hope they're not too boring and academic, but they show a lot of really interesting information. So let's just look at breaking down temperature in a few other ways, looking back to 1940 at Portland Airport. We're going to do this by season. So this is the winter average temperature. Each red circle is every winter's average temperature. Winter is defined in this case as the months of December, January, and February. Winters have been warming, as this black line shows, but not all that fast. And then this blue line is the trend of the most recent 30 years. The dashed black line is the most recent 30-year average, and the blue line is the average of the entire record going back to 1940. So we've seen an increase in winter temperature, but it's really, really noisy. We still get cold winter days, or sorry, cold winter years. But we haven't seen anything quite as cold in a while that we've seen back here. 2017 was actually pretty cold. And again, this is also just Portland Airport, but things will look pretty similar around Northwest Oregon and the Pacific Northwest if we look at other cities. In spring, things warm a bit more than winter, a little faster. But summer is when we've seen this huge amount of warming. In the last 30 years, this blue line shows the fact that it's much steeper than this black line means the last 30 years have been warming faster than the overall 83 or so year period that we have going back to 1940. And the distance between the black and the blue line here is pretty large for summer. So summers have been warming fast, and so have falls, but there hasn't been as much of a recent acceleration in fall warming as we've seen for summer. So this goes to the most recent summer, which was the third warmest on record in Portland. Last summer, despite the heat dome in June, was the second warmest by a small fraction. 2015 is still the warmest summer. Interestingly, if I did this for the months of July, August, and September, it would stand out like a sore thumb. It would be so far above the other years, averaging July, August, and September. This past July, August, and September has been so exceptionally warm in Portland. It stands way out. I just don't have that plotted here. And October is almost certainly going to be the record warmest October in Portland. We've broken something like 9 daily high temperature records in Portland this October. September was the warmest September on record by, I think, almost 2 degrees. And August this year was the warmest month on record period in Portland. So not just the warmest August, but the warmest month. So the reason that this last summer wasn't the record is because June was relatively cool. Looking at cold days, cold temperatures, we talk a lot about heat because heat's dangerous. Heat can cause fatalities. Heat's something we care about. We know heat's increasing with global warming. What about cold? Well, as expected, cold is getting less cold. So the coldest night of the year is plotted here for every year. Here was that -3 in 1950. It's warming slowly, but overall, the coldest night of the year is not as cold as it used to be. We still get pretty cold. 2017, we got down to 11, but it's happening less often. The number of days that fall below freezing has been steadily declining. That's a pretty substantial trend. So we get much fewer days where some point during the day, the temperature drops below 32 degrees. And we're getting much fewer days where the temperature never gets above 32 degrees. So we get way fewer days on average with below freezing high temperatures. So warm's getting warmer, cold's also getting warmer. Cold is not getting more extreme because of global warming. It's getting less extreme. We can still get extreme cold. It's becoming rarer, and that extreme cold is less extreme cold than it used to be. And the reason for that is the Arctic is the fastest warming part of Earth, and the Arctic is the birthplace of our cold air. So the Arctic is warming faster than things are warming here, so that the factory for cold air is producing less cold air. So when we get that extreme cold air from the Arctic, it's just not as cold as it used to be, and it's warming pretty quickly. All right, a couple more things I want to show. We're going to try to go through these pretty quickly. There's a lot of charts. I have a few maps. Looking at extreme heat, this is another place where we have really interesting and very clear evidence of warming. This is the annual number of days over 85 degrees. The last 2 years tied each other for the most in Portland. And the number of 90 plus degrees, still 2018 is the record. We came pretty close this year. Last year, we're actually quite a bit lower, even though we had the 3-day stretch of record shattering temperatures in June. Looking at the hottest day of the year, just another way to look at this, it's getting warmer. This is 2021, so that changes the whole scale. The hottest night of the year, interestingly, we broke the record in June 2021, But we also almost got that warm in 1941. So 1941 had some pretty impressive heat waves too. And then the annual number of days over 100 has been increasing, but we have yet to break the record of 5 days. So even this year and last year, Portland only had, well, I say only, had 5 days above 100, but we also did that in, I think, 1975 and 1941. And it was 1975, if I'm not mistaken, where we had 5 of those in a row. So we haven't done that recently. Of course, last year we broke 110 in Portland twice, which has never been done before. Rainfall is not interesting as far as trends go for observations. So I try to break this down into as many ways as possible to look at it. The mean annual precipitation rate is telling us when it rains, how hard does it rain? That's kind of declining, but it's not significant. So it's not raining more intensely, at least at the daily scale. The number of days with rain has remained unchanged, just with lots of variability. The number of days where it rains over 1 inch has declined a little bit, but again, not really significant. And the maximum annual 1-day rainfall, meaning how much rain fell on the day that had the most rain of each year, no trend at all, totally flat. So we're not yet seeing any change measurably in our rainfall in Portland. And that's true in Northwest Oregon overall. That's a little less true if you go to like Southwest Oregon. There have been some decreasing trends there. Let's look at this more geospatially. Now we're looking into the future. We're not looking at trends anymore. We're looking at what to expect in the future. Now, these are maps showing from these climate models that we run with these scenarios of future changes in greenhouse gases and ask them to show us how the climate changes. This shows how much warming occurs by the end of the 21st century, but I'm not showing the values here. You can see there's no color bar. I did that on purpose because the values aren't actually important. These models were run using this very high-end emission scenario that's probably unlikely to happen, and some of the models warm too much. What I show this for is to show that the interior parts of the Northwest are projected to warm more in the summer than the coastal parts, and that in some of the interior places, this is the extreme heat. Extreme heat warms more than the average heat, at least by this measure. It's not quite so true for Portland, and we certainly aren't seeing that clearly in observations. But by the end of the century, under continued warming, in some of the Northwest, the most extreme heat will warm faster than the less extreme heat. So that's a challenge. When we look at things more closely by season, this actually is showing values. This is summer warming by the end of the century under this very high-end emission scenario, and this is winter warming. They're on the same color scale. So all these reds are like 5 or 6 degrees Celsius warming. Portland is kind of in this orange of 4.5 to 5 degrees. But for winter, it's only about 3 degrees. I say only, that's still pretty big warming, but winter warms at a much slower pace in the Northwest than summer. That's already the case, as I showed with the observational evidence. That will continue into the future. So winters are just not warming as fast. Other parts of the world, there are reasons that the winter's warming faster, but that's not the case here. And then let's look at what we expect rainfall to do in the future. Again, this is under this very high-end warming scenario by the end of the 21st century. So it's not saying what's happening now or what's going to happen in 10 years. It's saying if we really ramp up global warming in 70 years, what are we going to see? So it's showing us like how the system responds to warming, maybe not exactly what specifically we should expect on any given year. So this is winter precipitation. Everywhere that's green is projected to get wetter. So we see these big increases as a percent of winter rainfall in the dry parts of the Northwest. So the dry areas actually have an increase in precipitation that's greater than the wet areas. The rain shadow effect that is so important here in the Northwest, it gets a little bit weaker, these models tell us. And there's some interesting research going on at Oregon State into understanding why by someone named Nick Seiler. But everywhere gets wetter. And in the summer, everywhere west of the Cascades gets drier. We're already pretty dry, but periodic summer rains can be really important for slowing down wildfires. So losing that is a concern. And then interior parts of the Western US actually are projected to get wetter in summer as the northwest monsoon gets more active and comes further north. This is kind of out of place here. I just wanted to look at snowfall really quick. It's kind of hard to think about snow when it's been so hot. I sometimes hear people say Portland's getting more snow than it used to, but that's not true. Portland's actually getting a little bit less snow over time. If you go back to the 1800s, which I don't have a chart here for, Portland used to get a lot of snow, and it's declined steadily since. Over the last 80 or so years, the decline in snowfall in Portland has been fairly minimal. This looks like a big decline in snowfall, but it's because in the 50s, there were so many snowy years, it kind of visually messes things up. And snowfall rate hasn't changed, so it's not like it snows harder when it snows. Portland gets some years with snow, some years without snow. Every once in a while, we get a lot of snow. The problem with Portland getting snow is when it does snow, it's a huge problem because we're not very good at dealing with it because it doesn't happen too often. Okay, last couple of slides here. I want to talk just very briefly about some of my research and something that we're focusing on, I think is really interesting, are these types of weather patterns that bring warmer than average and drier than average temperatures. High pressure ridges, they're called. They're kind of boring weather patterns because they're like the opposite of storms, but they've been so important. They're always important in the Northwest, and they're a normal part of our climatology, and they're a normal part of the climatology of the mid-latitudes in the Northern Hemisphere and the Southern Hemisphere. But they can be very, very impactful. And when they get extremely strong in the summer, we get heat waves. And so this is a map of pressure in the middle part of the troposphere, halfway up through the top of the atmosphere. And it's showing this big dome of high pressure over British Columbia during the June 2021 heat wave. This is what's called the heat dome. It's a big dome of hot air over the Northwest. And under that dome, air sinks. And as air sinks, it thermodynamically warms. It also prevents clouds from developing. We looked into how this sinking air played a role in this heat wave, and it was really, really important. But in the wintertime, these domes of high pressure are important because they cut off the storm track when we get dry stretches in the winter. They're also really important for our air pollution. So the reason it's been so polluted in Portland the past couple of weeks is not just because we have wildfires, it's because we've been stuck under a seemed like a never-ending high pressure ridge. So these are really important. And we want to know, is climate change making them more common or more frequent? It sure seems like it. This whole fall has been characterized by one. The summer we had these, the heat dome last June. Last winter, most of January and February were dry in the Northwest because we had a ridge of high pressure. So we went to our climate models and asked them, by season, are we going to see more or fewer of these ridges? And here's winter, and everything that's blue means fewer ridges. Everything that's green or yellow means more. And the X's mean that the signal is significant. And we see winter, a pretty big area of decreases in the number of days with the high pressure ridge. We see the same thing in the spring. In the summer, when these ridges cause heat waves, we see this increase in the interior, mostly centered over Montana, but we don't see a significant increase over the Northwest. So this tells us that, and this is under the extreme warming scenario. This is not contemporary. This is like worst case scenario in 70 years. You're really ratcheting up the warming, and we don't see an increase in the type of weather patterns that caused last June's heat wave. And in the fall, we see a decrease as well. So what this tells us is that, at least according to this experiment, those weather patterns aren't becoming more frequent. We also looked into their strength. They're not projected to become stronger, but when they occur, it's just hotter. So when you get a dome of high pressure, that causes hot air, but now it's even hotter. And there have been a couple of papers that have come out on the June heat wave that have estimated between 0.5 and maybe 2.5 to 3 degrees Celsius of warming added to that heat wave because of climate change. That sounds pretty small. Like, well, didn't the heat, this kind of, or might think the heat wave happened because of global warming, but the heat wave was estimated at anywhere from a 1 in 1,000 to 1 in 100,000 year event, but it was made more severe because of global warming by a couple of degrees, and that's actually pretty significant. So it still would have been a record-breaking heat wave, but it was that much more record-breaking. And if that heat wave pattern happened, if this happens in 50 years, you can add another couple of degrees to that. Now we're talking about temperatures in Portland around 120. So seems like a small amount of warming is actually pretty meaningful, but it doesn't mean that the heat wave itself or the heat dome is caused by human-caused climate change. It was just made worse because we're shifting that histogram. Everything's going to the right. This is like the worst slide ever because it's all text. So I think I'll say one quick thing. This is about how to assess whether a weather event may or may have been made more likely or more severe by climate change. And the key is to ask these two questions. Is the event part of a long-term trend? Because climate change is a long-term shift in the climate. It's not a step function or instantaneous thing. And is a change in the probability or severity of that event consistent with physical expectations of climate change? So anything related to heat, the answer to that is yes, because we know global warming is making everything hotter. So if you get a yes to both of those questions, climate change pretty likely played a role. If you don't get a yes to both of those questions, it doesn't mean climate change couldn't have contributed to it, but the answer is not super obvious. And to really answer these carefully, you really need expert assessment. And there are scientists who've made this their expertise. So I have just a couple of conclusions here, just summarizing things, but I think I'll stop there because it's almost 8 and I hope there's some time to answer some questions. And I see there's a question in the chat. Do I share my data with agriculturalists in the Northwest? So all the data I showed here is publicly available. So I'm taking this mostly from either published papers or like the temperature and precipitation data. That's all from NOAA, from National Oceanic and Atmospheric Administration, or from NASA. So everything there is publicly available. Some of those I took the data and I plotted it in ways that I wanted to, but there are lots of web portals where people can find this for themselves. So I haven't created any data to share with the public because it's already publicly available data.
I'd like to point out that I've got everybody muted right now. So if you want to ask a personal question, or not personal question, but a question, please unmute yourselves so you can ask that question.
Hi, it's Charles Hall here. I really enjoy watching the NASA television channel, and so much of it has to do with looking at warming. For example, there was quite a bit of work done in Iceland having to do with the layers and so forth and so on of warming, as I understood it. But it's fascinating information, and it's nice to see that NASA is very involved in that.
NASA was originally created to observe the Earth from space. So being kind of in the NASA family myself in the earth science world, I'm always happy to promote NASA's earth science and earth science observing, because it's pretty amazing what we're able to measure from space because of NASA satellites. It's incredible.
It's fascinating.
Yeah.
So, Paul, down in the Colorado River country, where the water is such an extremely low problem now, do you foresee that there's going to be any solution to that?
So I wouldn't say I have deep expertise on that particular topic, but my understanding is one of the big problems there, and this is true across the West, which is, we didn't talk about drought, but the West is, I think, pretty confidently considered in a mega drought at this point, which do occur every couple of decades or centuries, but it's made worse because of warming. And the Colorado River problem is more an issue of warming temperatures than it is of lack of rainfall and snowfall, although snowpack is declining as winter temperatures warm. But part of the problem that's happening is because temperatures are so warm, or getting so warm, the ground dries out. And when there is runoff from snow melt or rainfall towards the rivers, a lot of that rain just goes to replenishing the soil moisture, and it's not making it into the Colorado River system. That's kind of troubling because the West has been in a dry couple of decades. That will at some point reverse, and it will be a wet couple of decades. But as temperatures keep increasing, there's going to be more evaporative demand on the soil and on the ground. And so even that increase in rainfall due to a wet period or increase in snowfall, if it's cold enough, probably won't be enough to bring the amount of water into the river system that had been there when temperatures were cooler. There are people who know more about this than me, though, so I don't want to go too much further into that. But I do want to, just a theme there, a lot of the impacts and challenges related to climate change can really be directly, or maybe not always directly, but pretty close to directly related to temperature. I think sometimes temperature is overlooked because warming doesn't sound that severe. We want to talk about extreme storms and destruction and all that, but warming temperatures have a really big impact and should not be underestimated. And they could be kind of subtle like that. Just drier soil, it absorbs the water, so that water going into the river.
Thank you.
Unmute yourself, Yvonne. You're muted. Yvonne, you are muted.
Still muted.
Yep, there she goes.
What do you advise us to do for this coming winter in the Portland area?
Well, seasonal prediction is very hard. And we have a little bit of information that we can use to make some very rough seasonal predictions, but weather forecasting is pretty good out to about 7 days. It's okay out to about 10 days. And then when you get to this 2-week to 10 to 20 year period, it's really hard. We can sort of project climate beyond 20 years if we know how greenhouse gases are going to change, but anything at that seasonal to decadal timescale is really hard. But we have some things that we can go on, and that's namely what's going on in the tropical Pacific Ocean. And that's where El Nino and La Nina events occur. La Nina being when it's cooler than average, the ocean surface temperatures there. El Nino when it's warmer, and then neutral and it's in between. This is the third La Nina year we've had in a row going into this winter, which is very unusual. That doesn't happen too often to get 3 in a row. Overall, our winters are cooler and wetter than average during a La Nina. But last year, our winter was drier to about average. Temperature wasn't especially cold. And then the previous winter, I'm trying to remember, we had some cold weather. We had the ice storm in February. That was also a La Nina. So it's hard to really make these confident projections. But if you look at the statistics, the odds would favor cooler and wetter than average winter, but there's no guarantee of that.
Thank you.
Mm-hmm.
When you take a look at the increasing ocean temperatures and the increasing atmospheric temperatures, that also increases the amount of evaporation off the ocean, correct?
Right.
And it seems like we're seeing quite a few of those channels of water coming out of Hawaii towards. Is that something that we can expect to see more of?
Yeah, so those are called atmospheric rivers, and then I think you're referring to the Pineapple Express flavor of atmospheric rivers, the ones that tap into subtropical moisture near Hawaii. So there's a lot of research on atmospheric rivers and climate change, and my lab group is part of that. So first of all, we have not seen any change in atmospheric river frequency or intensity at this point in the Western US. Atmospheric rivers happen all over the world, but in the Western US, we haven't seen that in observations at this point. But as the atmosphere and the ocean get warmer, like you said, the atmosphere can hold more water vapor, so it can evaporate more ocean water, and it can hold more water vapor. So atmospheric rivers are defined as corridors of high amounts of water vapor being transported, and then when that's lifted, it can cause heavy rainfall. Atmospheric rivers are pretty confidently expected to get bigger and juicier. They might not get stronger. The wind is probably not going to get stronger, but they'll be wetter. But that doesn't always translate into more rainfall because you have to efficiently lift that additional moisture. And that's where things get really complicated. So we know atmospheric rivers are going to they're going to carry more water vapor. They're probably going to be larger in actual size. They're not going to be more frequent because they're just a part of regular storms. And there's no indication that the number of storms will increase, could even decrease. What that translates to in rainfall is a little complicated, but here in Oregon, there's pretty good confidence that the most extreme rainfall events, which all occur from atmospheric rivers west of the Cascades, will get more extreme as things warm. But we're not clearly seeing that yet. There's some evidence that those floods that happened near Surrey last November in southern British Columbia, northern Washington, they were really severe. There is a study that attributes, says with climate change, that was more likely than it would have been in the past. It's just one study, but that could be an indication that while we don't see the trend yet, maybe it's starting to emerge. But that's kind of, we'll have to see, how that evolves.
It's also interesting that during the Pleistocene, of course, there were several different ice periods as well as warmer periods, but the ice periods tended to be precursor by pluvials, by extreme amounts of rainfall. So it's might be interesting to see how this eventually works out if we are seeing more evaporation, more water content in the atmosphere, if that translates to rainier periods that would then, I don't know how that affects the climate necessarily, but it would suggest that it actually cools the climate, could cool it substantially.
Yeah, so I don't think there's any evidence that increase in rainfall would be enough that would counterbalance the greenhouse warming. It would just be an amplification or an acceleration, I should say, of the water cycle. One kind of just interesting side notes on that, in places that get extreme rainfall through thunderstorm type rain, which is not how we get it here in the Northwest. So like the southeastern US, places that get tropical rain, that deep convection, those deep clouds make really good use of that added water vapor and evaporation. And it's they're already clearly seeing increases in the intensity of extreme precipitation. Here in the Northwest, our heavy rain actually happens in really shallow layers near the surface, so it's a bit different. One other thing I just thought of too, related to that, is the drivers of atmospheric rivers are not really ocean surface temperature, although that can add evaporation. They're driven by horizontal temperature gradients. So really the difference between the cold Arctic air and the warm tropical air. And as the Arctic warms faster than the tropics, those gradients are weakening. And so that's actually, it's those gradients that really create those rivers. The evaporation kind of adds juice to them. So there's a lot of moving parts.
Another one.
Well, I see a question there about can you say something about the future trends in the Northwest snowpack?
Yeah, that's a good question. And I didn't have a slide here on that. Northwest snowpack is broadly and confidently projected to decline, and pretty much, in most aspects. It's not declining as fast as one would expect in the recent observations, but it is declining, and that's likely the result of some natural variability working in the opposite direction of warming temporarily. that's kind of preserving some of our good snow years. Projections are really confident that, especially in the Oregon Cascades, where most of the snow falls at relatively low elevation, where it's pretty warm, that increasingly snowpack will become less reliable, will start later in the year, melt earlier in the year, be less consistent throughout the year. At really high elevations in the Northwest and much colder places like the Wallowas or the Northern Cascades or the Rockies in Idaho and Montana, those places would hold on to snow probably till the later part of the 21st century still. But in these lower elevation regimes like Oregon has, that's likely to be a fairly rapid loss in the next couple of decades. Still, we'll have some good snow years like we did last year, but there'll be fewer and further between. And years like 2015, where there's almost no snow, will become more common, especially around like mid-century. That starts to really show up in the projections. That's a concern for sure.
Great. You have any more questions out there? Better chime in now. We've asked Paul to stay pretty long here.
That's okay.
Jane has a question. Jane Walpole.
I was at a master gardener seminar about 4 years ago. A hydrologist was there, and he said that but that the general feeling was that by, say, 2040, latest 2050, the firs and the pines would be gone from the Willamette Valley, and you'd only find them on the flanks of, the highest mountains that we've got around here. Have you heard anybody talking about anything about it being that severe?
I have not. That I don't know a ton about climate change and ecology, but that sounds pretty extreme to me. So I'd be surprised that was likely to happen in that time frame.
I'll go with what you said.
Sorry, I didn't hear the last comment.
I said I'll go with what I like your information better.
Yeah.
I'm not hydrologist.
Yeah.
I had another question. And that was, you used the base of 1850 to 1900 as a base for human activity and climate change. And that was a period that was well prior to the introduction of the automobile, well prior to the introduction of internal combustion engines and things of that nature. What is the time period for the Industrial Revolution?
So the pre-industrial period, which is also often used. So I didn't choose that 1850 period. That's kind of a standard one that's used in other studies. But sometimes we use prior to 1750 to have really no effect. So I think really before coal burning. Yeah.
Okay. Yeah, coal burning was going on at that point in time.
Right.
And also steam was being used in farming, for example, as steam factors and things like that.
Yeah, driven by coal, I think mostly. Yeah.
Driven by coal. Okay, thank you.
So Yvonne has a question.
This is always new to me. What about earthquakes that we keep hearing about recently offshore? Any and Mauna Loa just about to erupt. Should we be concerned about earthquakes over here?
Well, so that doesn't have anything to do with climate change. So it's kind of outside of my wheelhouse. Those are not connected phenomena. My understanding is we should be concerned about earthquakes here, but I kind of leave that to the seismologists to talk about. Volcanic eruptions can affect the climate, but the climate does not affect volcanic eruptions.
Thank you.
Charles, we may have come to the end of our questions. Do you think we ought to go ahead and wrap up a little bit?
Sure, absolutely. I want to thank Paul. That was some of the best information I have ever seen
Oh, thank
on
you.
climate change. And I tell you that's a game changer, Paul. And I want to thank you so much for sharing that with us today. And I'm really glad to know that it's public, and so forth and so on. But I also want to throw a big thank you to Lloyd Decay, because we've had two folks leave our board because they're moving out of Oregon, and that would be Rick Thompson, our president, and our secretary, Sylvia, his wife, and Sylvia was a real whiz at running these Zoom meetings. She really had it down pat. And in that regard, I want to thank so much to Lloyd Decay for trying to help me understand how to do this. And I'm still not sure I got it, but I did lose power and I had to re-log in, and I felt pretty proud that I got back in without any help from anybody. No phone calls, no nothing. I did it. Yes. That was indeed something. But I want to thank Lloyd very much for being our producer and our host tonight, and he's so kind to do that. And we really value our relationship with Paul. We also really value our relationship with Tualatin Heritage. And I want to just say that I was myself and Mark Buser founded the Lower Columbia chapter in 2005. And it was when we heard about what IAFI was doing with regard to the National Ice Age Trail and so forth and so on. And then in 2012, we then created a relationship with the Tualatin Heritage, which we really value. Tualatin Heritage Center. And Yvonne is very involved in that and so forth and so on. And the idea was we would share the thing about keeping programs going on the third Thursday of every month, which is tonight, and really having fascinating speakers over the years. And so we're getting pretty old here, as we are in person as well as for the chapter, and we're looking for new members. We want new members to come in. We want to expand our board, and basically we think that we've got something going here that is really incredible, because the floods have done so much. For example, in the fertilization of the Willamette Valley, to be one of the most fertile valleys in the world, with the loess that sits on it, because it was a settling pond so often when the water would back up and couldn't make its way all the way through the Columbia and out into the Pacific. That's just one example. So the floods had a real impact in this area. So the next meeting talks about glaciation, and I think it's very appropriate. Andrew Fountain will be speaking on glaciation. His title is Scientific Discovery of Glaciers in the American West, Their Current Conditions and Probable Future. And it ties right into what we talked about tonight. We see glaciers getting smaller and disappearing and so forth. And so that's going to be a very exciting meeting. It'll be on November the 17th at 7 p.m. Again, it will be a Zoom meeting. And then December, the third Thursday is so close to Christmas, we never meet. And so then we pick up again on the third Thursday in January of 2023. And we intend to continue what we're doing and keep exploring, because this is so relevant to how we live on this beautiful earth that we have.